All right, so now that we've talked about acids and bases and being able to determine the pH of an acid or a base, we're now going to look at when acids and bases react with one another. And we've actually already looked at this when we looked at double replacement reactions, but let's just quickly review. So when you add an acid and a base together, you get what's called a neutralization reaction. So a neutralization reaction is an acid and a base. It's going to form water and then a salt. So let's see that. So here's your example, sulfuric acid and sodium hydroxide. So this is a double replacement reaction. So sodium and sulfate are going to form a compound, and H and OH is going to form H2O. So sodium has a +1 charge, sulfate has a 2- charge, so that's going to form Na2SO4. And then H and OH will form water. Now I just need to quickly balance this. Since I have 2 sodiums on my product side, I'm going to put a 2 in front of NaOH, and then I now have 4 hydrogens on my reactant side, so I'm going to put a 2 in front of water. So that's all you have to do. It's a double replacement reaction, an acid and a base reacting together, you form a salt. So in this case, your salt is sodium sulfate. Remember, a salt just means an ionic compound. It does not necessarily mean NaCl, and water. Okay? So let's look at some calculations that we can do with acid-base reactions. So we're going to be working on titrations. So in a titration, what happens is in that burette there, and that burette is that long tube right there, that burette will have a base in it, okay? And in that Erlenmeyer flask is an acid. And to that acid, I have added phenolphthalein. Now, phenolphthalein you've already worked with before, but phenolphthalein, just as a review, turns pink when it is exposed to a base. So what happens if you look at this graph here, if you look at 0, where I've added 0 volume of NaOH, the only thing that is in that Erlenmeyer flask is HCl. Then, as I move from left to right along this graph, notice the pH is increasing. And the pH is slightly increasing because what happens is that NaOH that is being added is going to react with the HCl. And it's going to neutralize the HCl. Okay? And that is why slowly but surely the pH is increasing. Then all of a sudden you see this huge jump in pH. And so what has happened right there is halfway in between this jump, so right around 10 milliliters, that is when your concentration of your acid equals the concentration of your base. And we call that your equivalence point. Okay? At that point, if you notice, your pH is going to be 7 because I have equal amounts of strong acid and strong base. Once I'm past that point, then I no longer have any HCl. All of it has reacted with NaOH. And so as I continue to add NaOH, I'm just adding NaOH, which is causing my pH to increase until it reaches the maximum amount, which would be the pH of just straight NaOH, which would be right around 11. Okay, so notice what happens is as I add the base, once I hit that equivalence point, my pH is going to be 7. So you're actually not going to see a change in color at a pH of 7 or at your equivalence point. So instead, you're actually going to see a change in color at your end point. And your end point is simply the point at which your color changes, the color of your indicator changes. So because phenolphthalein doesn't turn color until you have a basic solution, you have to go slightly past your equivalence point in order to reach your end point. Okay? So when we're doing this lab, we're going to assume that our end point and our equivalence point are the same, because once we know that our concentration of acid and base are the same, once our moles are the same, then we can do the stoichiometry we're about to do. However, you do need to keep in mind we're slightly off because when you actually hit your equivalence point, the solution is still going to be clear. We have to slightly pass your equivalence point in order for the solution to turn pink. So, if we look at this problem, this shows us the whole purpose of titration. So in titration, as I said, you take an acid and you add a base to it. Well, why? Why would you do that? Well, here's the thing. You know the concentration of your base. You know the concentration of that solution that's in that burette right there, in that tube. and you know the volume of base. We'll figure that out in a second. But if you notice from the graph, the base that was required to reach equivalence point was 10 mils. So you know the concentration of your base. You know the volume of your base. You can use that graph, or I could just tell you, okay? I also know the volume of my acid. And so what this allows us to do, titration allows you to determine the concentration of an unknown substance. So the whole point of this titration is to determine the concentration of your acid. Okay? So let's look at this example problem. It says a 25 ml sample of HCl is placed in a flask. So you can see that in the picture above, with a few drops of phenolphthalein. If 32.6 milliliters of a 0.185 molar NaOH solution is needed to reach the end point, meaning we're going to assume that that's the equivalence point, what is the concentration of HCl? So at your equivalence point, we know that I have equal moles of NaOH and HCl. Okay? So what that allows me to do is to use a mole-to-mole ratio to go from moles of NaOH into moles of my acid, and that will allow me to determine the concentration of my acid. So let's look at this. The first thing you need to do, though, is you need to write out your reaction. So HCl is reacting with NaOH, and that produces NaCl, right, because those are my innies, that's my salt, and water. Now notice I'm actually already balanced, so that makes my life easy. Now I'm going to start with my 32.6 milliliters of my NaOH. Okay? I'm going to want to figure out my moles of NaOH so then I can then determine my moles of HCl and therefore my concentration of HCl. Keep in mind, guys, the whole concept of endpoint and equivalence point is new, but we actually have already done concentration stoichiometry. We've done this before. Okay? I'm going to now put milliliters on bottom so that I can get into liters, because remember the units for molarity are moles per liter. So 1 liter is 1,000 mils. Now I'm going to get into moles by putting liters on bottom and moles of NaOH up top. My concentration of NaOH is 0.185 moles for every 1 liter. Okay? Now I'm in moles of NaOH. Since I'm at my endpoint or my equivalence point, I know that my moles of NaOH equals my moles of HCl. So I can simply use a mole-to-mole ratio. Moles of NaOH on bottom, moles of HCl up top. It's a 1-to-1 ratio. Finally, since I'm asking for concentration, what I can do is I can put liters on bottom, okay? And that would actually, since everything cancels except for moles of HCl and liters, that would give me concentration because it's moles per liter. So I'm going to put the volume of HCl that I have, which is 0.025 liters, because I converted 25 mils to liters, and 1 on top. Okay, so that's all you have to do, and your concentration that you get is 0.241 molar. Okay, so the whole point of titration is to use a solution of known concentration, reach your equivalence point to figure out how much of that solution you need, so that you can then do the stoichiometry to determine the concentration of your unknown solution.